Welcome to lesson 6.4, where we're going to use identities to help solve trigonometric equations. So the nice thing about this section is that there is nothing new for us. It's just a combination of everything we have seen regarding trig and general solutions and solving equations. So it's not just chapters 4, 5, or 6, but also the trig that you did in both pre-cal 11, math 11, and I guess really grade 10 as well, and everything we know about solving equations. So we might see some factoring or see some of the techniques we need with polynomials to come into play as well. So we're going to start with this first question. We'll start in the same way we normally do, in that if I was doing a proof or looking at simplifying an expression using identities, I'll write things in terms of sines and coses. And then if we're not careful, we're going to make a mistake that we have to be very, very careful about in terms of solving for solutions in an equation. And we'll look at how we can fix that mistake and then run through everything that we know. Now, the very first thing I'm going to do before we start solving is take a look at non-permissible values. So there's nothing that shows up on the left side of the screen, on the left side of the equation. On the right side, we get secant. If secant of x is equal to 0, we would have non-permissible values. And also, if I look at the tan, I will also have an undefined function if cosine of x is equal to 0. So if secant is equal to 0, that gives us 1 over cos is equal to 0, which gives us 1 equals 0 if I multiply by cos, which doesn't make any sense because there are no values of x where secant will be undefined. However, if I look at cos of x equaling 0, we know that tan will be undefined anytime cos of x is equal to 0. And that, of course, is going to happen at pi over 2 plus pi k k-e-i. Okay, now I could have just looked at my tan function and understanding where the asymptotes were, and I could run through and do that if I wanted to. All right, let's take a look at this equation then. So there's something we need to do on the left side here. So we'll get sine cubed of x. Tan is sine over cosine. So tan squared will give me sine of x squared over cos of x squared. That's just being multiplied by the cos of x. If you want to, you could write that as cos of x over 1. So the 1's acting just as a placeholder there as we multiply through. Secant is 1 over cos of x. So as I start simplifying things can actually simplify very nicely for me. In the numerator, we can probably see that one of those cosines is going to cancel. But if I look now at the fraction I have in the numerator and the fraction I have in the denominator of both of those fractions is cos of x, right? I have a sine squared over cos of x in the numerator. Right, so that would be that fraction here up top. And then I have a 1 over cos of x in the denominator. And what's going to happen is the 1 over cos of x and the 1 over cos of x are going to cancel. So I'm left just with sine squared x in the, on the right side at that point. Now, we have to fight the urge. So we're going to do two things here. We don't want to do what I'm about to do. We have to fight the urge to divide by sine squared on both sides, which would leave me with, well, sine cubed divided by sine squared would give me sine of x. And then sine squared divided by sine squared would give me sine of x is equal to 1. And of course, that's going to happen at pi over 2 plus 2 pi k k-e-i. Now, the reason why we have to fight the urge to do that is because we need to find all of our solutions, and we find our solutions by factoring. So I'm going to start by subtracting sine squared from both sides, and hopefully you were thinking about this already. What I miss if I divide by the sine squared of x instead of factoring it out, because it's now a common factor in sine cubed x minus sine squared x, when I factor out that sine squared of x, that gives me sine squared times sine minus 1. And I miss this first solution. I miss that sine squared of x is equal to 0, which means that sine of x is equal to 0. And that, of course, is going to happen at pi k e I. And just draw my unit circle up here. I'm looking for the points where sine is equal to 0. I'm left with another solution as well. So I get sine of x minus 1 is equal to 0. So that leaves me with sine of x is equal to 1. And of course, we've already actually solved that, right? That's pi over 2 plus 2 pi k e I. Okay, now, before we sort of leave it there and put a big circle around our last two lines there, we have to realize that my non-permissible values take care of the solution for sine of x equals 1. Right? Those are non-permissible values. Now, we don't want to do what's over here in the black ink anyway, right? We don't want to do, let's put a larger box around this. We don't want to do this because by not factoring out the sine squared, we miss the solution where sine of x is equal to 0. If I went through and took that first approach, I would look at my values of x and I would say that there are no solutions for that equation because the only solutions I found are non-permissible values. So there are values that mean I cannot evaluate the equation that I was given. However, when I factor out the proper way and I get that factor of sine squared x equals 0, that leaves me with the solution that x is equal to pi k for the equation. Sine cubed of x is equal to tan squared of x times cos of x divided by secant of x. So I need to make sure that I indicate that the values that are non-permissible values aren't actually solutions. All right, let's move on to our next example. So in this example, I need to find the general solution in radians for this equation. So we're going to rewrite in terms of sines and coses. So we know that cosecant is 1 over sine of x. Now, anytime we want to find a variable, one of the first things we normally do is get that variable up in the numerator, So let's multiply everything by sine of x to make sure that I'm not left with any unknown terms in the denominator. And so that's going to give me 2 sine squared of x is equal to 7 sine x minus 3. That looks awfully familiar. It seems to be a quadratic. So let's subtract everything that's on the right side from both sides of the equation. So I get 2 sine squared x minus 7 sine x plus 3 is equal to 0. I'm going to let u equal sine of x. And that's going to give me 2u squared minus 7u plus 3 equals 0. So if I factor that, factors of 6 that add to -7, and I can definitely do that. So I'm going to get a 2u minus 1 and a u minus 3. You can do decomposition if you want, or you can run through and do inspection. I know that both signs in the binomials have to be the same because I have a positive sign in front of the 3. I know they have to both be negative because I have a negative sign in front of the 7. And then I just need those factors of 6 that add to 7. That would be, factors of 6 that add to -7, and that would be -6 and -1, which I get as my cross terms. By solving that factored quadratic, I get 2 sine of x minus 1 is equal to 0, and I get sine of x minus 3 is equal to 0. That, of course, I guess maybe we should go one more line. We could write it as sine of x is equal to 3, and there are no solutions that exist for that equation. If I add 1 to both sides, I get 2 sine of x is equal to 1. Divide everything. I'm just going to squeeze this in here at the bottom. Is equal to 1/2. So I'm looking for those points. Again, we're looking for the general solution. So I'm going to get pi over 6 and 5 pi over 6. I didn't quite leave myself enough room there. Plus 2 pi k KEI. Now this time, before I move on, I'm looking at that solution to see if I've missed everything or if everything's all right. This time I forgot to look at my non-permissible values. So before I move on, I'm going to go back and I'm going to check those non-permissible values. So if we forget it at first, that's all right, as long as we get back to it near the end of the question. I can see that I'm going to have non-permissible values when sine of x is equal to 0. I'm going to solve for those values, but looking at the end of my solution, where I'm solving for sine of x is equal to 1/2, I know that these non-permissible values aren't going to play a role in that final answer. Right? So I get for the places where sine of x is equal to 0, that gives me pi k KEI. And those, of course, don't include pi over 6 and 5 pi over 6 plus 2 pi k. So that is all there is for that solution. All right, last question. So far, all we've really seen is using a couple of identities to simplify things. We've got one last identity that's going to come up in example 3. This one's a little harder to recognize, but we have to think a little bit more about what's happening. This question, example 3, is already in sines and coses. So if it's in sines and coses, I need to then go to my formula sheet and I need to think about some of the other identities I might be able to use. So maybe it's one of the Pythagorean identities, maybe it's a sum and difference, or in this case, it's a double angle identity that I want to look at. I'm going to recognize that if I multiply both sides by 2, I get 2 sine x cos x is equal to 1. And that 2 sine x cos x, we hopefully recognize as the double angle identity for sine. Well, I can take the inverse sine of both sides here, and I get 2x is equal to, so again, I'm looking at where sine is equal to 1. So that's going to be at 90 degrees. There's only one place on the unit circle where that is going to be true. So I get 2x is equal to 90 plus 360k, KEI. I divide everything by 2, which gives me 45 degrees plus 180k, KEI. There are no non-permissible values in this question. So there's nothing that we need to worry about in terms of the non-permissible values piece. Oh, let me just put that solution back in. There we go. All right, so that is the end of our lesson. If you have any questions, please make sure you have them ready for our next class. And there is a Delta Math assignment for you to complete before our next class.